Welcome back to the course Basics of Mechanical Engineering 3. I am Dr. Amandeep Singh Roy from IIT Kanpur. I am going to take tutorial session on mass transfer and applications. In this lecture, I discussed about heat transfer, I discussed about more tutorials in the previous weeks. This is mass transfer and applications such as boilers, heat exchangers or condensers, etc., for which we will try to calculate the efficiency. First, let me talk about mass transfer. Mass transfer, to recall the concept, is the movement of molecules or chemical species from one location to another, mainly due to concentration gradients. It occurs in processes like diffusion, absorption, distillation, drying, membrane separation. Main mechanism here are diffusion or convection. Diffusion is random movement from high to low concentration. Convection is transfer by bulk movement of fluids. Importance in engineering in mass transfer is, it is used in chemical, mechanical and environmental engineering fields, key to design chemical reactors, separation units and many industrial operators. You can see here distillation, let mass transfer go, absorption, let mass transfer happen. Then there is an extraction from a solvent to solute, and here you can also see through drying itself, through convection also mass transfer is happening. To talk about the parameters or key determinants of mass transfer, we need to understand Fick's first law of diffusion, which says Na by A, this is molar flux. It is written here, Na by A is molar flux, which is in kilomole per meter square second, in which area is A, that is meter square, then Na is molar flow rate, that is kilomoles per second. This is equal to D times the concentration gradient, that is the difference in the concentration of the two medium which are in discussion, that is C1 minus C2, where C1 is high concentration in moles per meter cube and C2 is low concentration in moles per meter cube, by L, the length through which mass transfer is being discussed upon, that is length of mass transfer, L in meters. Now, mole fraction of gas is given by X gas is equal to P gas by P, where P gas is partial pressure of the gas, T is the total pressure of the gas. Molar concentration of each gas, if we need to see, this is concentration of the gas, molar concentration. C gas is molar concentration of gas, which is equal to P gas by RT. And this we saw the gas law, it is taken from that only, where R is universal gas constant, whose value is 8.314 kilojoules per kilomoles. When we talk about molar concentration, we shall also discuss about mass concentration and mass fraction. Mass concentration, that is rho gas, is equal to C gas into capital M gas, where capital M gas is molar mass of the gas and rho gas is mass concentration. Let us be very careful. C gas is molar concentration of gas, rho gas is mass concentration, which is the product of the molar concentration into the molar mass. Mass fraction is W gas, this is mass fraction, is rho gas by rho, that is mass concentration of gas by total mass density. Let me try to see a problem and we will use these relations. It says a vessel contains a binary mixture of oxygen and nitrogen with partial pressures in the ratio of 0.21 and 0.79. At 15 degrees, the total pressure of the following mixture is 1.1 bar. Calculate the following molar concentration, mass fraction. So, it is a mixture of gases, that is oxygen and nitrogen, at 15 degrees centigrades. Partial pressures are given. Partial pressure for oxygen here is 0.21 and for nitrogen is 0.79. Now, what we have in the given data, partial pressure of oxygen, that is partial pressure of oxygen to the total pressure ratio, this is 0.21, and partial pressure ratio of nitrogen gas, our total pressure is 0.79. And they say the mixture that is obtained here, for this the total pressure turns out to be 1.1 bar, 1.1 bar, which is equal to 1.1 into 10 raised to power 5 pascals. Temperature is 15 degrees centigrade. To convert this into Kelvin, this becomes 15 plus 273. This is equal to 288 Kelvin. Now question is molar concentration, mass concentration and mass fraction. To find molar concentration, now we know PO2 turns out to be 0.21 into P, which is equal to 0.21 into 1.1 into 10 raised to power 5, which is 0.231 into 10 raised to power 5 pascals. Similarly, for nitrogen, it is 0.79 into P, which is equal to 0.79 into 1.1 into 10 raised to power 5. This is 0.869 into 10 raised to power 5 pascals. Now for molar concentration, I will try to find concentration of oxygen and concentration of nitrogen. So this molar concentration is, from the relation you could see, is the partial pressure of gas by R into T. So I will put this formula: CO2 is equal to P for oxygen by RT. Value of R I will put here, and temperature I will also put. So this is the calculated value, 0.231 into 10 raised to power 5 by R into T. Value of R I showed you here is 8.314 kilojoules per kilomole. So that means it is 8314 into the temperature 288, which is equal to 9.65 into 10 raised to power minus 3 kilomoles per meter cube. For nitrogen, this is partial pressure for nitrogen by R into T. Putting the values, this is 0.869 into 10 raised to power 5 by 8314 into 288, and this value comes as 0.036 kilomole per meter cube approximately. Second part is to find mass concentration. Third part is mass fractions. Now to find mass concentration, that is P for oxygen, that is C for oxygen times the mass for oxygen, where this capital M is molar mass. Putting the values, this is equal to 9.65 into 10 raised to power minus 3 for oxygen. Putting the value of molar mass 32, this is equal to 0.309 kilograms per meter cube. Why is this 32? Because we know for oxygen molecule oxygen molecule has O2, that is oxygen plus oxygen, which is 16 plus 16 is equal to 32. Similarly, for nitrogen, we have 14 plus 14, that is equal to 28. This is for nitrogen. Therefore, the mass concentration for nitrogen would be C for nitrogen times the mass of nitrogen, that is molar mass. This is 0.036 into 28, which is equal to 1.033 kilograms per meter cube. Then next part is mass fractions. Mass fractions simply I will put W for oxygen is equal to P for oxygen by total P, and W for nitrogen is equal to P for nitrogen by total P, where what is value of P? This P is equal to partial mass of oxygen plus partial mass of nitrogen. This turns out to be 1.342 kilograms per meter cube. Therefore, mass fraction is 0.309 by the total, that is 1.342. This is equal to 0.230. This is fraction. There are no units here. For nitrogen, it is 1.033 by 1.342. This is 0.769. This is of the resulting mixture, the mass fraction that we have gotten. So, there is another problem statement. It says a thin plastic membrane separates hydrogen from air. The mole concentration of hydrogen in membrane of inner and outer surface is 0.45 and 0.002 kilomoles per meter cube respectively. The binary diffusion coefficient of hydrogen of operation temperature is 53 into 10 raised to the minus 10 meters square per second. Find the mass flow rate of hydrogen by diffusion through the membrane and at standard temperature if the thickness is 2 mm, secondary thickness is 0.5 mm. So, I will calculate it for case 1, case 2 I will leave it for you. So, what is the problem statement? We have a plastic membrane in between. This is, for instance, a plastic membrane. And we have inner surface and outer surface. This is, let me call inner side, outer side. This is plastic membrane. It is hydrogen on both the sides here. What we are given here is value of D, that is diffusion coefficient, as 53 into 10 raised to the power minus 10 meters square per second, and C1 and C2, which are the concentration towards the two sides of the membrane, which is 0.045 kilomole per meter cube and 0.002 kilomole per meter cube. Now, we need to find mass flow rate of hydrogen by diffusion. to find the mass flow rate. First it says for 2 mm thickness, which means I will put first case where T is equal to 2 mm. So, we know molar flux, that is Na by A is equal to D times C1 minus C2 by the length. Putting the values here, this is equal to D is 5.3 into 10 raised to the power minus 10, C1 minus C2 is 0.045 minus 0.002, this by L, that is thickness, that is 2 mm. 2 mm is 0.002 meters. I will put it here, 0.002 meters. This value turns out to be 1.139 into 10 raised to the power minus 8 kilomoles per meter cube. This is molar flux. Then mass flux. We have gotten Na by A. Mass flux is but it is flow of the mass, which is m dot A by A. This is equal to molar flux into the mass, that is Na by A into the molar mass. The element here given is hydrogen. So, this is equal to the calculated value, that is 1.139 into 10 raised to the power minus 8 into hydrogen, 2 molecules, per molecule mass is 1 into 2. This is 2.278 into 10 raised to the power minus 8 kg per meter cube. This is for thickness 0.02 mm. Second part very similar to this, when the thickness is 0.5 mm, that is 0.0005 meter. This you can calculate by yourself. I will just give you the answer. Answer is 9.116 into 10 raised to the power minus 8 kgs per meter cube. Now, I will talk about applications of thermodynamics such as heat exchangers, boilers, condensers, etc. What are heat exchangers? Let us recall the concept. Heat exchanger is a device that transfers thermal energy between 2 or more fluids at different temperatures. It is a crucial component in numerous applications, from heating and cooling systems to power generation and industrial processes. Heat exchanger effectiveness is also epsilon, which measures how well a heat exchanger transfers heat compared to the maximum possible heat transfer. That is, epsilon here is Q, that is actual heat transfer by the heat exchanger that is designed, per unit the maximum possible heat transfer. Here you see heat exchanger, it was hotter before, it is cooler after, or it could be cooler before and hotter after. Heat exchange could happen in any direction. For a heat exchanger, certain parameters which are taken into account for the design are hot outlet temperature of the fluid, that is temperature hot, that is outlet, is equal to temperature of heat exchanger in minus Q by Ch, where Ch is the heat capacity of the hot fluid, which is m dot h into Cph. M dot h you know is mass flow rate, and Cp we have discussed about in the previous lectures. Cold outlet temperature, that is Tc for cold outlet temperature, is the Tc in, that is in temperature, plus Q by Cc. So, here Ch and Cc are the heat capacity rate of hot fluid and the cold fluid respectively. Heat transfer can be given as Q max is equal to C minimum times the difference in the temperature, that is hot inlet temperature and cold inlet temperature, where C minimum is the minimum heat capacity rate of the fluid, Th in is the inlet temperature of the hot fluid, Tc is the inlet temperature of the cold fluid. Let me take one problem statement here. Two fluids A and B exchange heat in a counterflow heat exchanger. Fluid A enters at 420 degrees centigrade and a mass flow rate of 1 kg per second. Fluid B enters at 20 degrees centigrade and also has a mass flow rate of 1 kg per second. Effectiveness of heat exchanger is 75%. Find the heat transfer rate when specific heat of fluid A is 1 kilojoules per kg Kelvin and that for fluid B is 4 kilojoules per kg Kelvin. So, this is a problem where we have a kind of a setup. In this is a heat exchanger and there is hot end and cold end. This is temperature of cold end inlet, that is given as 20 degrees. It says the fluid enters at 20 degrees. This is 20 degrees centigrades and from the cold side there is outlet temperature. Then from the hot side there is outlet temperature and from the hot side there is inlet temperature which is given as 420 degrees centigrades. Here we have cold fluid and we have hot fluid. From here temperature flows and from here also the temperature flows. It says it is a counter flow heat exchanger, therefore, this is from left to right cold, then the hotter would be from right to left. Then they say we have mass flow rate, that is m dot c. This is equal to 1 kg per second and here also it is same. This is equal to 1 kg per second. Now, given these variables, we also have specific heat of fluid A as 1 kilojoules per kg Kelvin, that is Cp for hot and this is Cp for cold. So, temperature T C inlet is 20 degrees centigrade which is 293 Kelvin, T hot in is 420 degrees centigrade which is 693 Kelvin and we have seen that m dot C is equal to m dot H which is equal to 1 kg per second and we have Cp values here. Also it says effectiveness is 75%, therefore epsilon is 75% which is equal to 0.75. Find the heat transfer rate, they say. To find the heat transfer rate, let me first see heat capacity rate. Heat capacity rate is Ch, that is m dot H into Cph which is equal to 1 into 1 and this is 1 kilowatt per Kelvin. Heat capacity for the colder portion is m dot C into Cpc, this is equal to 1 into 4, this is equal to 4 kilowatt per Kelvin. Therefore, C minimum is C hot, that is 1 kilowatt per Kelvin. Maximum heat transfer heat capacity rate, then maximum heat transfer, this is equal to Q max, this is equal to C minimum into the difference in temperatures, the difference in the inlet temperatures, that is temperature of hot portion inlet minus temperature of cold portion inlet, which is equal to 1 into 693 minus 293, this is equal to 400 kilowatt. So, this is what was asked in the question. They asked about the heat transfer rate, or what is the heat transfer here. To find the actual heat transfer, you could also do, I am just leaving it for you. So, this is step 1, this is step 2. Step 3, I will try to calculate the actual heat transfer. Actual heat transfer, we know epsilon is equal to Q by Q max. Therefore, Q is equal to epsilon into Q max. This is equal to 0.75 into 400. This is equal to 300 kilowatts. So, with this, we have calculated the actual heat transfer. That is, they asked about the transfer rate. One more thing you can calculate, I am just leaving it for you. You can say, you can also calculate the fluid outlet temperature. This TH outlet is equal to TH inlet minus Q by CH. These values you know, and similarly you can find TC outlet, that is T cold outlet, is equal to T cold inlet minus Q by C cold. This you can calculate further. I will come to the next application, that is boilers. Power plant boilers are large vessels that heat water to create high pressure steam, which then drives turbines to generate electricity. They are crucial component in thermal power plants, converting fuel into a usable form of energy. Boiler efficiency measures how effectively a boiler converts fuel into usable heat. Its ratio of the useful heat output to the total energy input is the boiler efficiency. So, this is a boiler setup. This we have discussed in the previous lecture. Professor Ramkumar has already discussed it. Now, first law of thermodynamics for a steady flow process, that is steam generation, says Q minus W, that is heat minus work done, is m dot times H2 minus H1. This we have discussed when we talked about enthalpy, entropy. For a boiler and condenser, when W is equal to 0, that is no shaft work is there, Q is equal to m dot into H2 minus H1. The mass of the fuel required is calculated by m dot is equal to Q in by CV, where CV is a calorific value of the fuel in kilojoules per kg, depending upon the fuel that we are using. Are we using coal? Majorly the coal is used, depending upon the kind of the coal that is there, hard coal, soft coal, depending upon the calorific value, the mass of the fuel is calculated. Now, let me come to a problem statement for a boiler. It is about a simple efficiency thing here. Boiler operates at 85% efficiency and produces 10 tons per hour of steam with an enthalpy rise of 2500 kilojoules per kg. If the calorific value of coal is 30,000 kilojoules per kg, determine heat required per hour, heat input needed, coal consumption per hour. They say there is a boiler system here in which heating is done. From here heating is done and steam comes out. They say steam comes out at 10 tons per hour rate, and delta H is 2500 kilojoules per kg. This I have put a solid base of the boiler. Now, parameters given are eta is equal to 85%, that is 0.85. M dot, that is mass flow rate, is given as 10,000 kg per hour. Delta H is given as 2500 kilojoules. And calorific value of coal is also given, which is 30,000 kilojoules per kg. Now, first part, heat required per hour. Heat required per hour is simply the product of the mass flow rate into the enthalpy. First is heat required per hour. This is equal to Q output, which is M dot into delta H. This is equal to 10,000 into 2500, which is 25 into 10 raised to power 6 kilojoules per hour. Next point is heat input needed and coal consumption. Heat input needed, I'll put eta is equal to Q output by Q input. We know the value of eta, therefore Q input is Q output by eta, that is efficiency, which is equal to 25 into 10 raised to power 6 by the efficiency 0.85. This value turns out to be 29.41 into 10 raised to power 6 kilojoules per hour heat input. Then it asks about coal required, the coal consumption. Coal consumption, that is mass of coal required is equal to heat input per unit calorific value of coal, which is also given in the question. Heat input we have calculated 29.41 into 10 raised to power 6, and calorific value is given as 30,000 kilojoules per kg. Therefore, we get the mass of coal required, that is coal consumption rate here is 980.33 kilograms of coal per hour. Coal consumption per hour. Coal consumption also I will put it here, per hour is asked. So, this is all calculated. Next, I will talk about condensers. A condenser is a heat exchanger that converts exhaust stream from the turbine back into liquid water, that is from hot to colder part. This process is crucial for maintaining a low pressure environment in the turbine, enhancing its efficiency and recovering water for reuse in the steam cycle. Condenser mechanism you have already talked about. I will just come to the problem statement directly. The calculations are very similar to what we have done for the heat exchanger and the boilers as well. Here the problem says steam is condensed from enthalpy of 2200 kilojoules per kg to 200 kilojoules per kg at a rate of 2 kg per second. Cooling water has a specific heat of 4.18 kilojoules per kg Kelvin, water enters at 25 degrees centigrades and it exits at 35 degrees centigrades. Find the required mass flow rate of cooling water. It says there is a condensing system, or I'll call it a condenser, that turns steam into water. So there is steam entering in, I will say steam in and steam out. This is a condenser. We have water in and water out. The temperatures are given. Water enters at 25 degrees centigrades. I will put it as T1 is equal to 25 degrees centigrades and it exits at 35 degrees centigrades. I will put T2 as 35 degrees centigrades, and it says the steam is condensed from enthalpy of 2200 kilojoules per kg to 200 kilojoules per kg. So here enthalpy H1 is 2200 kilojoules per kg and H2 is 200 kilojoules per kg, and it is also given the mass flow rate 2 kgs per second. I'll put m dot for a steam, that is here is 2 kg per second. So let me put all the variables which are given. We have H1 as 2200 kilojoules per kg, H2 as 200 kilojoules per kg. Mass flow rate for steam is given as 2 kg per second. T1, T2 is given, which is 25 degrees and 35 degrees respectively. Now we convert into Kelvin or do not convert, it doesn't matter, because in all the calculations we would have to calculate delta T only. So I'll put here delta T is equal to 35 minus 25 is equal to 10 degrees. Then they have given specific heat of cooling water, that is Cp is equal to 4.18 kilojoules per kg Kelvin. Find the required mass flow rate of cooling water. To find the mass flow rate, let me first try to find heat removed by condenser. That is Q steam is equal to m dot steam times the change in enthalpy. This is equal to 2 into 2200 minus 200. This is equal to 4000 kilowatts. This was step 1. Now step 2 is water cooling capacity. Water cooling capacity. Here heat lost by steam is absorbed by water. I will say heat lost is equal to heat absorbed. Heat lost by steam is absorbed by water. Therefore, Q steam is equal to Q water, and we know Q water is equal to mass flow rate of water times Cp, that is specific heat of water here, times the temperature gradient. Therefore, mass flow rate of water is equal to Q of water by Cp into delta T. Putting the values, this is equal to 4000 by 4.18 into delta T, that is 10. This gives me the mass flow rate of water as 95.693 kilograms per second. This is mass flow of water per second here. With this, my lecture is closed, and I have covered the heat transfer, mass transfer and applications of thermodynamics in these two tutorials. I will talk about the virtual laboratory setup in the next lecture, where I will talk about the heat transfer systems and try to see some experiments in the virtual environment. Thank you.